So to find the length of the curve, we're going to look at 2 points on the curve, x1, y1, and x2, y2, and we're going to find the distance between those points by doing the square root of the distance between x squared plus the distance between y squared. Distance between x is delta x, and distance between y is delta y. You can see that on the graph. Dividing both terms by delta x, we get 1 plus delta y squared over delta x squared. And just changing delta y over delta x to be written as dy dx. So the distance for one segment is the square root of 1 plus delta y over delta x squared. And to see in a visual, if we were to just look at one segment, but we could break this up and look at many little segments. So to sum up an infinite number of segments, looking at the limit as delta x goes to 0, making those segments as small as possible, summing up the distance for one segment, you can see that that's really representing the length, which is the integral from a to b of the square root of 1 plus dy dx squared dx. So using the arc length formula, we're going to use y is equal to x squared on the interval from 1 to 3 to find the length of the curve. The length is going to be the integral from 1 to 3, square root of 1 plus dy dx squared dx. So we need dy dx, we have y is equal to x squared. To get dy dx, take the derivative, which is 2x. Replace that into the function, so we have integral from 1 to 3 of 1 plus the quantity of 2x squared dx, and then using the calculator to get the answer of 8.268. For the next example, we're going to find the length of the curve y is equal to 1/3 x squared plus 2 quantity to the 3 halves on the interval from 0 to 3. So use the length of the curve, integral from 0 to 3 of the square root of 1 plus dy dx squared dx. So we need to get dy dx. Take the derivative, we're going to use chain rule. So dy dx is equal to, bringing that coefficient in front, we get 1/2 x squared plus 2 to the 1/2, and multiply by the derivative of the inside, which is 2x. Then rewriting the problem, bringing that back into the arc length formula. The integral from 0 to 3 of 1 plus the quantity of x radical x squared plus 2 squared. Simplifying, get the integral from 0 to 3 of the square root of 1 plus x squared times x squared plus 2, the radical canceling out. Then distributing to get 1 plus x to the 4th plus 2x squared dx. Just rewriting the problem so that we can see that we can factor. So we have x to the 4th plus 2x squared plus 1 under the radical. And that can get factored as the quantity of x squared plus 1 quantity squared. Square and the square root will cancel out, so we have the integral from 0 to 3 of x squared plus 1. Then anti-deriving to get 1/3 x cubed plus x from 0 to 3. Then following the fundamental theorem of calculus, replacing in the value of 3 and replacing in the value of 0. Then calculating and simplifying to get the answer of 12. The next example, we're going to find the length of the curve y is equal to x to the 1/5 from the points negative 32, negative 4 to 32, 4. So taking the derivative, we get 2/5 x to the negative 1/5. But notice that the derivative does not exist when x is equal to 0. X is equal to 0 is on our interval from negative 32 to 32. So if we look at a sketch of the curve from negative 32 to 32, we can see that we have a vertical tangent line at x is equal to 0. So in order to avoid this problem, we're going to go ahead and get the inverse of the function. So we'll switch our x's and y's. And by solving for x then, we're now going to have a tangent line that's horizontal, so we won't have a problem of a vertical tangent line. So solving for x, we get y over 2 is equal to x to the 1/5. Raising the fifth to both sides, we get y to the 5th over 32 is equal to x. So taking the derivative of x with respect to y, x is equal to 5 over 32 y to the 4th. So then L is equal to the integral from negative 4 to 4, 1 plus dx over dy squared dy. So the integral from negative 4 to 4 of the square root of 1 plus 5 over 32 y to the 4th squared dy, and then using the calculator to get the answer of 67.172.